Hello and welcome to yet another video of this channel. In this playlist, we are learning about how to solve linear differential equations, right? Ordinary differential equations to be more general. And in this video, we are going to learn the algorithm to solve a general non-homogeneous linear differential equation with constant coefficients. Well, this is a this is a general algorithm that we are going to talk about in this video, and in the later videos we will see how we can actually solve a particular case of the non-homogeneous linear differential equation with constant coefficients. Okay, so the first step is to identify how does a non-homogeneous linear differential equation look like. So the first term you can see here is the nth derivative of y with respect to x. Y is the dependent variable, x is the independent variable, and it is linearly combined with the n minus 1th derivative of y with respect to x. The coefficient is k1, which is a constant, and the next term similarly is n minus 2th order derivative of y with respect to x, and the coefficient is k2, and so on till the last term, which is kny, where kn is a constant and y is the zeroth derivative of y with respect to x. So the zeroth derivative of any function is equal to that same function, and in this case, the variable, the independent variable is x, but y zeroth derivative is the function itself, and this is equal to r. Now this r is a function which is a function of x only, right? Because if this function contains y, our equation will no longer be a linear differential equation. It will become a nonlinear ordinary differential equation. We can convert that into a linear differential equation, but that is outside the scope of this video. Okay, the first step here is to find out the complementary solution, or you might also call that as a complementary function. So, the method to do that is to write down the auxiliary equation of our given differential equation, given linear differential equation, the homogeneous part of it. Please note that we have written the right hand side as 0, right? And we'll consider y as the dependent variable, and we will take the y outside. We shall substitute dn by dxn by capital D to the power n, and we will consider the appropriate cases 1, 2, 3. In order to understand what are the cases 1 to 3, please go back to the previous video and have a look at them. My, just as a revision, case 1 is the case where there are real roots and all the roots of the auxiliary equation are different from each other, right? They're distinct. Case 2 is the case where there are some of the roots which are equal to each other, but all the roots are real. Case 3 is the case when some roots could be complex but conjugate to each other. Okay, once we find the roots of the auxiliary equation and we have considered the appropriate case, we move on to the next step, which is finding out the particular solution or the particular integral, commonly known as PI. In order to find that, we take the r, which is the right hand side function of x, and we divide by fd. So this fd is a function of the operators. The differential operator d is d by x dx, right? Differential operator d is d by dx, and we extract all the coefficients and the order of derivatives from the given equation to write the functional description of this particular function, right? And this depends the function in the the division of r by f of d. This depends on what our r is and what our fd is. We will look we'll find more about this in the next videos. But this is how we find out the PI as a particular solution. Then the general solution of the given differential equation is given by the complementary solution that we have obtained in this particular step, the second step, and the particular solution in the third step. And to be more specific with the terminologies, we shall obtain the complementary function and the particular integral. So the summation of these two is going to give us the general solution. Thanks for watching. See you in the next video. Bye.